I see the Gaussian kernel equation. It shows how we calculate the similarity between two data points, x and y. The symbol represents the distance between them. The GAMMA parameter controls how quickly the similarity decreases as the distance between points increases. A larger GAMMA means similarity drops off rapidly for even slightly distant points. Think of it like this. A high GAMMA is like a very focused spotlight. Only points very close together are brightly illuminated, high similarity. A low gamma is more like a floodlight, illuminating a wider area, high similarity even for relatively distant points. This question is asking you to think critically about how changing the GAMMA parameter in the Gaussian kernel affects the results of the spectral embedding algorithm. It's like asking, what happens when I change the focus of my spotlight on the data? I'll explain this important concept. The affinity matrix is a square matrix where each element represents the similarity between two data points. In our case, this similarity is calculated using the Gaussian kernel equation with a specific GAMMA value. A higher GAMMA makes the affinity matrix sparser, meaning it'll have more zero values because distant points are deemed less similar. This affects how the algorithm groups data points together during dimensionality reduction. I see this as about the parameter GAMMA that controls the shape and width of the Gaussian function in our similarity calculation. It influences how much weight we give to nearby versus distant points. A small GAMMA considers points far away as similar, while a large GAMMA only considers points very close together. This statement says that by increasing the GAMMA value, we emphasize local relationships in the data. That is, points that are close together will be grouped more tightly together, while distant points will be less related in our reduced dimension representation. This statement is incorrect. As explained earlier, a higher GAMMA leads to a more detailed, less smooth embedding because it focuses on local structures. This statement is generally true. Because a larger GAMMA makes the similarity between distant points drop to near zero, it makes the affinity matrix sparser, containing more zeros. This statement is true because while a sparse matrix can be computationally cheaper, the increased precision needed to handle very small values with higher GAMMA might offset those savings, increasing overall computational time. This is the title of this question. We are examining how changing the GAMMA parameter in a Gaussian kernel used in spectral embedding affects the outcome. I'm focusing on how changing the gamma parameter in a Gaussian kernel affects the results of a spectral embedding. Think of gamma as controlling how picky the algorithm is about considering the similarity between data points. A larger gamma value makes the algorithm more selective, only considering points that are extremely close. A smaller gamma value makes the algorithm more tolerant, looking at points that are farther apart. This significantly impacts the final embedding. I'm assessing your understanding of how the gamma parameter in a Gaussian kernel used with scikit-learn's spectral embedding function affects dimensionality reduction. Remember, the Gaussian kernel measures the similarity between data points based on their distance. Scikit-learn, SKLEARN, is a popular Python library for machine learning. Spectral embedding is a dimensionality reduction technique using the spectrum of the affinity matrix of the dataset. Increasing gamma makes the kernel more localized, only nearby points are considered similar. This results in the final data embedding showing more local patterns. This is incorrect. Increasing gamma actually makes the embedding less smooth and more detailed because it strongly emphasizes local relationships. Increasing gamma makes the affinity matrix sparser because the similarity between distant data points becomes almost zero. The matrix will have more zeros and fewer non-zero entries. While a sparser matrix might seem computationally cheaper, the increased precision needed to handle the very small values resulting from a high gamma can actually increase computation time. It's a tricky trade-off. I'll help you see this. While there's no diagram, I can explain the concepts visually. Imagine a scatter plot of your data. With a small gamma, the kernel considers points far apart as similar, creating a smooth, blurry picture. A large gamma only links very close points, making the picture sharper, but potentially missing larger patterns. This is the core question. We're exploring how changing the gamma parameter in a Gaussian kernel used with spectral embedding affects the results. I'll guide you through understanding the impact on the embedding. Let's dive in. Increasing gamma makes the Gaussian kernel narrower. This means only data points very close together will have a significant similarity score, recorded as non-zero values in the affinity matrix. Points farther apart will have near zero similarity, leading to more zeros in the matrix and making it sparser. That's an important relationship. While a sparser matrix can sometimes speed up computation, the increased precision needed to handle the tiny values generated by large gamma can counteract this benefit. The algorithms may struggle with the small values, increasing the total computation time. It's a bit of a trade-off. This statement is incorrect. A larger gamma focuses on local relationships, resulting in a less smooth, more detailed embedding. It's like zooming in on a map. You see more detail locally, but the overall smoothness is lost. That's important to remember. This is true. A larger gamma makes the kernel sensitive only to nearby points. So, the resulting embedding will preserve local structures better. The result accurately reflects local data relationships. This question asks you to think about how changing the gamma parameter affects the results of a dimensionality reduction technique called spectral embedding, which uses a Gaussian kernel. Think about the Gaussian kernel function. It measures similarity between data points. Let's explore how gamma affects it. I see this statement. Increasing gamma means that the Gaussian kernel's width decreases. This makes the similarity between distant data points drop quickly to almost zero. This means the affinity matrix, which represents the similarity between all data points, becomes more sparse, meaning there will be more zeros in it. It's not always completely true, though, because it depends on the original matrix sparsity. I understand this statement too. While a sparser matrix could lead to less computation in some scenarios, with a larger gamma value, you need to deal with very tiny numbers in the computations. These tiny numbers can slow things down and, in many real-world cases, actually lead to increased computational cost. It's a bit counterintuitive. Let's look at the Gaussian kernel. It's a mathematical function representing similarity between two data points, x and y. The double bars, x, y, represent the distance between them, which is squared. Gamma is multiplied by this squared distance. The result is then exponentiated. Essentially, this function gives high similarity values when points are close and low values when far apart. Gamma controls how fast this similarity decreases. Gamma is a parameter in the Gaussian kernel. It controls the width of the Gaussian curve. A higher gamma means the curve is narrower, meaning similarity drops very quickly with increasing distance. A lower gamma means the curve is wider. Similarity decreases more slowly with distance. This is a matrix that shows how similar each pair of data points is. It's constructed using the Gaussian kernel. Each element represents the similarity between 2 points according to that kernel. This is a dimensionality reduction technique. It uses the affinity matrix to create a lower dimensional representation of the data, while trying to preserve important relationships between data points. I see the Gaussian kernel formula. It shows how similar two data points, x and y, are. The distance between them is squared, multiplied by a negative gamma, and then exponentiated. A larger gamma makes the exponent more negative, making the kernel value smaller, unless the points are very close. That means larger gamma values only give high similarity scores to points that are very close together. Let's talk about what happens when we increase gamma. Remember, gamma controls the width of the Gaussian curve. A larger gamma creates a narrower curve. This impacts how the spectral embedding algorithm sees the relationships between data points. The affinity matrix shows the pairwise similarities between data points, calculated using that Gaussian kernel. When I increase gamma, only points really close together will have high similarity values. Other pairs get near zero values. This creates a sparser matrix, fewer non-zero values. Think of it like this. Increasing gamma makes the affinity matrix more like a sieve, only allowing strong local relationships to show through. Because of this increased sparsity, I get a more localized embedding. The algorithm now better reflects local neighborhood relationships between points. The embedding will be less smooth. It will highlight details in local areas but may lose the big picture. Now, let's talk about the computation. You might think a sparser matrix is faster to process. But a higher gamma value means more calculations to determine those very small values near zero. This can lead to higher computational costs, depending on how the eigendecomposition is implemented. So, while sparsity can help sometimes, the extra precision needed for those tiny numbers can make things slower. I'm going to explain how increasing the gamma parameter in a Gaussian kernel affects the results. Think of gamma as controlling the reach of the kernel. A larger gamma makes the kernel focus on points very close together, ignoring those further apart. It's like shining a really bright but tiny flashlight. You only see what's right under the beam. This dramatically changes the way the algorithm groups data points. Because a larger gamma makes the kernel only notice nearby points, the resulting embedding emphasizes local structure. This is like creating a map where only nearby towns are connected, even if some distant ones are actually related. The algorithm will show clusters of closely related data points but might ignore global trends. It's a trade-off. We gain in detail but lose some global perspective. It's important to find the right balance depending on your data's properties. The affinity matrix is super important here. It shows how similar each pair of data points is, and that similarity is determined by the Gaussian kernel. A larger gamma means the similarity between distant points quickly drops to almost zero. This makes the affinity matrix much sparser. Fewer entries will be significantly different from zero. Most will be close to zero, showing low similarity. It's like a network where distant nodes have very weak connections. This sparsity impacts the later computational steps. I've already mentioned this increase in sparsity. To reiterate, think of it like this. A higher gamma creates an affinity matrix where only nearby points have strong connections, making it sparse with many near zero values. This could, potentially, improve the computational efficiency of some algorithms but not necessarily all. The increased precision needed to compute those tiny values can offset any gains from sparsity. I see the Gaussian kernel formula here. It shows how we calculate the similarity between two data points, x and y. The formula uses the distance between the points and a parameter called gamma. A larger gamma value makes the Gaussian curve narrower, meaning only points very close together will have a high similarity score. A smaller gamma will create a wider curve, resulting in higher similarity scores even for points farther apart. This simply means that a higher gamma value in the Gaussian kernel equation results in a narrower Gaussian distribution. This directly impacts how we measure similarity between data points. We're investigating what happens when you increase the gamma parameter within scikit-learn's spectral embedding function, which uses a Gaussian kernel. Spectral embedding is a technique used for dimensionality reduction, so we're asking how the choice of gamma affects the results. This statement is incorrect. Increasing gamma focuses on local relationships, resulting in a less smooth, more detailed embedding because it emphasizes local structure rather than a smooth global view. I agree. While a sparser matrix could lead to computational savings, a higher gamma value means that the computations involved in dealing with many very small numbers, which increases the computational burden. This is a dimensionality reduction technique that uses the spectrum, eigenvalues and eigenvectors, of a similarity matrix, the affinity matrix, in this case, to create a lower dimensional representation of the data. It's a sophisticated way to reduce the number of dimensions in your data while trying to preserve important relationships. This refers to the output of spectral embedding, the lower dimensional representation of the data after the transformation. The properties of this lower dimensional data, smoothness, detail, etc., depend heavily on the parameters used, in this case, gamma. These are the individual data instances in your dataset. Spectral embedding takes these points as input and projects them into a lower dimensional space. This is a crucial parameter in the Gaussian kernel that influences the shape of the Gaussian curve. As I explained before, a higher gamma value leads to a narrower curve and affects how we define similarity between data points. This matrix is computed using the chosen kernel, here, Gaussian. Each element, I, j, represents the similarity between data points I and j as determined by the Gaussian kernel. The affinity matrix is a key input to spectral embedding. This is the outcome of the spectral embedding, a representation of data in fewer dimensions. The properties of this reduced dimensionality data, such as its smoothness or detail, are influenced by parameters like gamma. This is incorrect. Increasing gamma will lead to a less smooth and more detailed embedding. Correct. A higher gamma means the kernel focuses more on nearby points, resulting in a more localized embedding. This is the overall topic. We're studying how the choice of gamma affects spectral embedding when using a Gaussian kernel for dimensionality reduction. This is generally correct. A higher gamma makes the affinity matrix more sparse because the similarity between distant points drops to near zero quickly. The outcome of spectral embedding. Increasing gamma alters the properties of this final data representation.